The last section is going to start talking about molecular formulas and hydrates. And to tell you the truth, molecular formulas is just going to be an expansion of empirical formulas. And actually hydrates, it's really a lot like empirical formulas, but what we're going to be doing is instead of just dealing with each individual element, you'll be dealing with compounds and water, and those are the only two things with hydrates. Molecular formulas. Okay, again, when you look at a molecular formula or a chemical formula, the thing is it tells you the exact ratio of the elements to one another. It tells you the elements that are present, but the most important thing is it tells you the ratio that they are in compared to one another. Comparing that to an empirical formula, remember an empirical formula was the simplest whole number ratio. So the thing is, when you look at C6H12O6, again, that's a molecular formula. That tells you that we are in a 6 to 12 to 6 ratio. But when you think of C6H12O6, I could actually reduce that down to CH2O. And that's what an empirical formula is. And there's actually lots of compounds that have the same empirical formula. Molecular formulas, that's going to be the final answer. That's going to be what the true compound actually is. A molecular formula is actually calculated from an empirical formula. What we're going to do is to get a molecular formula, you first have to calculate out the empirical formula, but what it's going to be is it's going to be multiplied by some whole number n value. Okay, so again, n will end up being a whole number. So for example, I was talking about CH2O, and I said, okay, maybe if we calculated it out, we get CH2O. But when I get n, I'm going to say that n is 12. And this molecular formula ends up being C12H24O12. It's just a different sugar. I know I talked about C6H12O6, same CH2O. So again, molecular formulas is what is going to be the real formula for that compound. Steps for calculating molecular formulas. The first thing that you have to do, you have to calculate the empirical formula if it isn't already given to you. Now I'm not going to include those steps because again, you have those steps already in your notes. So calculate the empirical formula from the steps that I told you initially. Now, to get that value of n, what you're going to do is you're going to take the molecular mass. Now, the thing I want to tell you about this is given in the problem. Molecular mass or the molar mass has to be given in the problem, divided by the empirical formula mass. So you're just going to add up the masses of all of the elements that make up that empirical formula. Okay, and also taking into account the ratios that they are in. And then the last thing you're going to do is multiply the empirical formula by the value obtained in step number 2. One of the things that I'm going to tell you from step 2, where you take the molecular mass divided by the empirical formula mass, and that's n, the thing I'll tell you is that will always be a whole number. You're not going to get any of those fractions. It will be close enough to a whole number that you can identify. And then, like I said, in step 3, take that whole number and multiply it by the empirical formula. Let's go ahead and look at this one. It says analysis of a compound reveals the compound contains 39.12% carbon, 8.76% hydrogen, 52.12% oxygen. It has a molar mass of 277.16. So the thing is, remember, I told you that's going to be that given. Okay, that's that molar or molecular mass. And it says determine the molecular formula for this substance. So as I said before, first thing you're going to have to do is you're going to have to take each one and convert it to moles. So 1 mole of carbon is going to be 12 grams of carbon. 8.76 grams of hydrogen, 1 mole of hydrogen is going to be 1.01 grams of hydrogen. And finally, 52.12 grams of oxygen. 1 mole of oxygen is going to have a mass of 16 grams of oxygen. So when I run that through, you're going to find out that carbon, using sig figs, 3.26. You're going to find out that hydrogen is 8.67. And when you do oxygen, it also is 3.26. Identify the smallest number. I have 2 of them up there. It's 3.26. So I'm going to divide everything by 3.26. Obviously, this one gives me 1.00. This bottom one also gives me 1.00. When I divide out hydrogen, I end up with 2.66. Okay, your next step for empirical formulas. Are they close enough to whole numbers? Well, 1 and 1 are whole numbers, but when I look there, 2.66 is not. That 0.66, we got to look back at our fractions. 0.66 is close enough to 2/3. And what I said there is, again, to make it a whole number, multiply by what the denominator of 2/3 is. So I'm going to multiply it by 3, and I'm going to multiply everything by 3. This one will end up being 3. This one will end up being 8, and oxygen will end up being 3. So my empirical formula is going to be C3H8O3. So I go to my next step. It says take the molar mass, 277.16 grams. We're going to divide it by. It said divide it by the empirical formula mass. So I need to get the mass of this thing right here. Okay, I have to figure out what the mass of C3H8O3 is. Carbon's going to be 36. 8 hydrogens, that's 8.08. And I've got 3 oxygens, that's going to be 48. So when I add all of those up, that ends up being 92.08. So I'm going to take that 92.08 and I'm going to put it down here. And when I divide that through, 3.01. That's the N that I was talking about. That equals N. So your last step said that you need to take your empirical formula, C3H8O3. Multiply that whole thing by 3. So carbon, 3 times 3, 9. So I've got C9. Hydrogen, 8 times 3. That's 24. And finally oxygen, 3 times 3, 9. My molecular formula is going to end up being C9H24O9. Let's go ahead and look at hydrates. There's a lot of times that compounds are going to crystallize from a water solution with water molecules attaching to the ions or the molecules that are part of that compound. What we're saying is take a compound and there's actually water molecules that stick to it. If any of you have ever seen some laundry soap, you see these little blue specks in it. Those little blue specks are actually little water molecules that are attaching to that laundry detergent, and those things are going to end up being hydrates. A hydrate is just going to be any compound where the ions or molecules have water molecules attached to it. Compound where the ions or molecules are attached to one or more water molecules. There will always be a specific ratio of water to compound, and it's usually going to be written like this: compound dot NH2O. So you're always going to have one of the compound dot, and then that N is just going to represent a whole number of water molecules that are attached to it. The other one that I used the other day in class, I used CuSO4.5H2O. What we're saying there is, for every compound of CuSO4, for every one CuSO4, we have 5 water molecules that are going to be attached to it. So 5 moles of water for every 1 mole of that compound. The name of this compound is going to be copper 2 sulfate pentahydrate. And what you're going to have to do is look on page 338 of your textbook. Table 11.1 has all of those prefixes that I'm going to need you to know for hydrates. To tell you the truth, it is very similar to chapter number 9 that we were looking at when we dealt with molecules or covalent bonds. Mono is 1, penta is 5, hepta being 7. So make sure again that you know all of those prefixes for hydrates. Let's go ahead and look at the steps for calculating hydrates. As I said in the beginning, the nice thing is you only have to worry about compound and water. And again, these steps are going to be very similar to the empirical formulas, but like I said, only dealing with compound and water. So what I'm going to say is, step number 1, you have to convert the compound to moles, and then you also have to convert the water to moles. Number 2, again, look at those 2 mole values. Look at the mole value of the compound, look at the mole value of water. Determine which one is going to be the smallest mole value. Step number 3, divide each one by the lowest mole value. So obviously one of them will end up being 1. The other thing that I want to tell you about this step right here is you will always get a whole number. There will be no fractions for hydrates. And number 4, it says write the formula of the hydrate. Okay, so if I go ahead and look at this sample problem, it says a hydrated sample of barium iodide has a mass of 10.407. Now here's the thing, when you look at that one right there, that 10.407, that is going to be compound and the water together. And again, if you think back to those notes that I told you, we want compound by itself and we want water by itself. Initially, that might look like an irrelevant number, but it's not. It says after heating the dry sample. Oftentimes you might hear the dry sample being called the anhydrous. Anhydrous also means dry. But it says after heating the dry sample of barium iodide, it has a mass of 9.520 grams. 9.520 grams. That is just the compound. And that's important because, again, that's what I want. I want to know the BaI2 by itself. It says, what is the formula of the hydrate? Now again, when you think back to your notes, it said, hey, you need to find the water. Well, here's the thing. If this number right up here, 10.407, if that's the compound in the water, and the 9.520 is the compound alone, if I go ahead and subtract those two, that will end up leaving the water by itself. So 0.887 grams will end up being water. Now there will be problems that you read through where it'll say compound has a mass of this, water has a mass of that. So you won't have to do this step. But if they give you the whole hydrated mass, you'll have to separate out the compound and you'll have to separate out the water by itself. So let's go ahead and look at this problem. We're going to go ahead and start off with our givens. Okay, so we have 9.520 grams of BaI2, and you have to convert that to moles. So 1 mole of BaI2, and that's going to be grams of BaI2. Next one is, we've got to take the water and convert it to grams. So 0.887 grams of water, 1 mole of water. When you add up the BaI2, you should end up with about 391.1 grams. Again, I'm just finding the molar mass of it. 1 barium, find its mass. Iodine, find its mass, take it times 2, and like I said, that should end up being 391.1. Water's one that we're going to be dealing with quite a bit. Water will always have a mass of 18.02 grams of water. So when I divide each one out, you're going to find out that the compound, or the barium iodide, is 0.0243 moles. When you divide out the water, you're going to find out that it's 0.0492 moles. Step number 2 says identify the smallest one, 0.0243. Dividing this one by 0.0243. Thing is, of course, that one will equal 1, and this one down here, the water will equal 2.02. Last step it says to do is to write the formula. We've got BaI2. There was only one of the compound. Dot, there ended up being 2 water molecules. If it said to name this compound, we would have barium iodide. When you look up 2 on that chart, it's dihydrate. So barium iodide dihydrate.